Welcome back to the module Forward Kinematics and Kinematic Transformations. Moving ahead, today we'll be doing a real industrial robot, which is a 6 degrees of freedom robot. So let us start with today's lectures. Let me introduce you to KUKA KR5 ARC robot. I'll be using this robot actually to demonstrate forward kinematics. So before we begin, let me just show the motion capabilities of this robot. So yes, it looks like this. By default, it has some orange type of color. Normally, all the industrial robots are bright in color so that in industrial environment, it is easily locatable and you can see the motions if it is making so that you can be safe. Okay, so now let me just color it with different colors so that it becomes easy to identify the links that I want to cover today. So yes, it is something like this. So here goes your first motion that it can do. So you see the bottom one on which it is mounted, the gray color over here is a static and that is mounted with some grouting bolts to the ground. So it is not going to move. The first link, the motor that you see it here, this is the motor that is actually giving it a vertical axis motion. Okay, vertical axis motion. So here it is. So it is making something like this. The second motion that it can do is, this is known as a shoulder joint. Okay. The first one was the base joint and this is the shoulder joint. You see, this is moving the yellow link which is there next. Okay. And then you have an elbow joint. This is an elbow joint. There is a motor over here to move it. This moves the purple colored link which is here. Okay. And then you have the axis 4 which is here, that gives you a motion that comes till the wrist. And you see axis 4 and axis 5 motion and axis 6 motion. That is a small tool which is over here, tool post that is moving. Okay, so I should make it like this so that it is easily visible to you. Okay, you see axis 6, it moves like this. So all the three axes are, it is intersecting at a point which is known as a wrist center point. Okay, so this is how it is. So let me come back to my original picture. Okay, so this is it. So this was your link 1. So you see you have link 1 which is here. So this whole assembly along with rest of the robot in assembled condition could rotate about this. This was the base frame. Okay, then comes the next axis which is here. So this was your first axis. If you can make a straight line over here. So this was your first axis. Next axis is something like this, you see. Okay, this moved this link. So this is your zero frame. Okay, zero frame which could be attached here. The first link is something like this. This is your second link which was moved by the shoulder joint which is here. The base one was vertically like this. Okay, now you have a elbow joint again, that is like the previous one. This is elbow joint that actually moves the arm which is here, arm which is extended right till the front. Okay, so this is axis 4. Okay, and then you have axis 5 that comes very much over here. Okay, so axis 4 can move it along this axis. Okay, about this axis you can make it rotate. This is axis 5 and then you have the last one which is here. Okay, that is the tool post. That is the tool post on which you mount all the tool, that is also known as an end effector. So you see you have a wrist center, inline wrist joint which is an intersection of axis 4, 5 and 6 together over here, and you have tool post which is here on which you can mount all the tool. Okay, so let us start doing forward kinematics for this. Okay, so here we go. This is your first base joint. So you have to have some reference frame fitted on it, that is, we'll call it as frame 0. The placement would affect the end effector position and orientation. Okay, so the first frame which is here, about which you will be expressing your end effector, you will be analyzing, you will be finding out the end effector position with respect to this one. Got it? So that is why placing of this frame is very, very important. So you see, if I place this as positive x-axis, so if your robot is right ahead, so it will show some positive x displacement if it is in that direction. So your coordinate, your end effector position will be based on the frame which is placed here. So this is very, very important frame. It can be preferably be placed on the floor. Normally we place it on the floor where the robot is, so that you can actually get the end effector position with respect to the place where it is grouted. Okay, not with respect to a point which is somewhere on a little higher up from the ground, so that it becomes very, very convenient to exactly locate your end effector position. And you know, all the robots which are there in the workspace, they all will be having this robot base frame. This is known as robot root frame. Okay, so this frame R1, R2, R3 and so on and so forth for all the robots will be there on the same floor. So that is the reason why it is so convenient to place it here. But anyway, you can place it anywhere along the axis. Okay, this frame is used to locate the robot among a set of other robots which are working together, as I told, with respect to the universal frame that may be somewhere in the workspace as well. Okay, the first link moves with respect to this frame. Now, because I know the next link which is going to come is going to rotate something like this, so I have placed my Z0 like this. So this becomes your Z0, about which your link 1 will rotate. Okay, so this becomes the axis of rotation for the first link. Now Z0 may be placed anywhere along this axis, as you know, but I have conveniently placed it here. Okay, and then X0 is placed along positive workspace. Normally I prefer putting it in this direction, so that I want to see all the time all the coordinates of my robot as positive. Okay, because I know my robot is going to be in this region most of the time. So every time it will be positive, at least along x-axis. Okay, Y0 is placed as per the right-handed coordinate system of axes. If you know where is your x, you know your z. So z cross x should give you y. So y is placed like this. So this is the reason why it is placed like this. So I prefer working with this one. Okay, the workpiece would be located with respect to the universal frame. So you know, now that I have placed it here, so universal frame is somewhere over here, that may be in this workspace. This was the robot frame. So workpiece will be located with respect to the universal frame or with respect to this frame. So when there is just one robot, it is this frame that becomes everything for the robot system. Okay, so let me just disappear so that you can read carefully. Okay, coming back. So yes, this is your next link. So now that I have already placed my first frame with Z0 like this. Okay, so now I'll move on to this one. Got it? Frame 1 is placed at the end of link 1, where you are going to attach your link 2. Okay, so link 2 will be moving with respect to the frame 1. So this becomes your Z1. Got it? If I can show you once again using this robot at least. So this was your first axis. So first frame, you see there is a motor here. There is a motor here that is going to rotate this link. Got it? So next axis will rotate along with the link 1. So this is this first assembly is your link 1, the brown one in the virtual figure you can see. So this is it. So this is your axis. So you got it. So this becomes your Z1. So now let us begin. So Z1 is placed along the axis of rotation of link 2. Got it? So this is your link 2. So this is your link 2. So that is moving with respect to link 1. That is this one, this brown one. This is your link 1. Okay. X1 is common normal to Z0 and Z1. So you see where you have to put X1. X1 is in red color over here. So this is a common normal to Z0 and Z1 directed away from Z0. So if it is Z0 like this, okay, and this is your Z1, so common normal is like this. So this becomes your X0. So it is directed away from Z0. So here it goes. So it looks like this. Got it? Now Y1 is obtained by using right-handed coordinate system. That is quite usual. So if you know X, you know Z, you also know Y using RH coordinate system, right-handed coordinate system. So distance measured along Z0 between X0 and X1. So where is your X0? This is your X0. This is your X1. So distance measured along Z0. So this is your Z0. So Z0 distance between them. So this is your distance is the link offset D1. So this is your D1. Got it? So this is your D1. Now distance measured along X1 between Z0 and Z1. Now find out where is Z0 and Z1. So again, this is your Z0. This is your Z1. And distance now is to be measured along X1. So this is here. So if you extend it behind, so it is intersecting here and here. So this is the distance. And what is this? This is length of the link, that is A1. So you got it. So this is your A1. Okay. Angle measured along X1. Angle measured along X1 using right-handed thumb rule to bring Z0 to Z1. So again, this was your Z0. This was your Z1. I have to bring Z0 to Z1. Z0 to Z1. That will become my twist angle. So you see it is rotating in counterclockwise direction. That is, if you measure it from here, so it has rotated like this. So that is your alpha 1. So by an angle that is 90 degrees. So that is your twist. Got it? Now, joint angle theta 1 is the joint variable because it is a revolute joint. So it is to bring X0 to X1. So already this is X0, this is X1. If at all there is any relative rotation between them, so it will be measured about this Z0, about this Z0, and angle will be theta 1. That will take X0 to X1. So looking from the top, if it is X0, this is X1, measured about an axis which is Z0. So this becomes your theta 1. Got it? Now, this is your first parameter table for the link 1, that is this one. This is your link 1. So D is distance that came somewhere over here. A is the link length that came here. A1. Theta 1 was the joint angle, that is the variable. Alpha is the twist angle. Okay, that was 90 degrees. So this is your base parameter for first link. Now you also should note frame 1 would move. This is your frame 1. Frame 1. So this frame, if this link rotates, frame 1 will rotate along with that. Okay, so that is what I meant here. So yes, now let us put the link 2. So this is your link 2. Okay. So it is, so frame 2 will be attached to link 2. So this is your frame 2 that is shown here. It can be placed at 2 different locations. Okay, so that is what I'll be focusing here to make you understand which one is better, which one is not. So Z2, first of all, you have to put Z2 along the axis of rotation of link 3. So this is your link. Okay, this is your link 3. So that is your axis of rotation, which is somewhere over here. Got it? So this is your axis of rotation, that is the motor. So that is moving. So this frame is to be put somewhere over here. Okay. So I have conveniently put Z like this. So this is your Z2. Got it? Now you have to put X2, that is common normal to Z1 and Z2. So this was your Z1. This is your Z2. So now you have to put X2. So X2 is nothing but it is common normal to this and this. You can place it over here, but I know this robot is a sagittal plane robot. That means there is a situation, there can be a situation when whole of this robot can lie in a plane. All the frames that I am going to put can lie on a single plane. Okay. So instead of taking it from here to here, taking it here and then bringing it back, it is better not to move it like this. Better not to move it in this direction and bring it back. Rather, I will just put my frames here and immediately here. That is in a plane. So irrespective of the shape of this link can be of any shape. Okay. This yellow colored link. So this frame is here, this frame is here. Link can be of any shape, but you have to put the frame here and another frame directly above that one. Okay, so that will be better. Okay, unnecessarily why to increase number of parameters if it can be directly eliminated right while you take the frames, while you place the frames. Okay, so X2 is common normal to Z1 and Z2. Y1 as per right-handed coordinate system as you have been putting so far. So this becomes your Y1. Okay, now D2 is measured along Z1 between X1 and X2. So where is your X1? So this is your X1 and you have X2 over here. So yes, there is no displacement between them along Z1. So this was your Z1. Okay, so this was your Z1 and there is no offset along that direction along Z1. So D2 remains to be equal to 0. But if at all you have taken this as a frame, then D2 would be displacement from here to here. So that is not the case. I preferably have put it like this. So D2 is equal to 0. Theta 2 is the joint angle measured between X1 and X2. So you have another angle, that is theta 2, that is the joint variable, that is going to be the angle between X1 and X2 in the given situation. This is your X1 and this is your X2. So already this angle is 90 degree. It is supposed to be like this, but it is like this. So it is already 90 degree. So that is the initial angle. That need not to be put. You can just put it as theta 2 in the DS parameter table. A2 is the distance which is measured along X2 between Z1 and Z2. So this was your Z1, this was your Z2. So this is your A2, that is the link length. Got it? And then alpha 2 is equal to 0. As you see, there is no twisting between Z1 and Z2. Z1 is parallel to Z2. So there is no twist along X1. So alpha 2 is equal to 0. So this becomes your new DH parameter in DH table. Okay, D2 is not equal to 0 in case second one is the case. If this is the case, D2 is not equal to 0. Okay, otherwise you will have to put the D2. Okay, so this is your DH parameter. Now, simplify the kinematics while placing all the frames. As I have said, D2 can be taken as 0 if you put it like that. So that is what I meant here. So let us move ahead. So now putting the third link. Now I have put the third link. Okay. See what is to be done. Now your robot, you know, you already have fitted your link like this. Now your fourth link is able to move like this. Okay. So this is your wrist. This can move like this. So fourth axis, actually the frame sits here, but it can be anywhere along this line. Okay, why not conveniently put it here so that it gives you the same effect. See, this is the consequence of putting it in two different locations. So I know the next link, which is here, next link that comes next is going to rotate something like this. Okay, so I have started moving it from here, conveniently placing my frame somewhere over here. So let us just begin. So Z3 along the axis of link 4. So link 4 that comes next, okay, which is going to rotate like this. So it is along the axis. So this is your Z3. Okay, so that will rotate your link 4. Got it? So that is your Z3. So that is conveniently put here. This was your 0, this was your 1, this was your 2, this is your third frame that I have placed just now. Okay. Now, X3 is common normal to Z2 and Z3. X3 is common normal to Z2 and Z3. See how it can be placed now? So this is it. So now there exists the common normal. So if this is your Z2, you know, and this is your Z3, so common normal do exists. So this becomes your X3. So this becomes your X3. This is the point of intersection. That is your frame 3. So this is very, very easy to understand in that case. It can conveniently place it here. That would be wrong also. So I'll tell you as it comes. So Y3 is as per the right-handed coordinate system. I have placed Y3 just like this one. Okay. And then D3 is measured. D3, that is the offset measured along Z2 between X2 and X3. Now find out where is your X2 and X3. So this is your X2, it's again X3, both are in same direction. So D3 is measured along Z2. Where is your Z2? 0, this was 1, this was 2. So this was your Z2. Okay, and this was your Z3. So there is no distance, there is no offset along that side, you see. Okay, there is no offset. That is the beauty why we have put my frame, initial frame here, because the next frame that I am going to put, it is going to be here. So this was my second frame. So this is your third frame. Both are one over the other. So there is no D3. Otherwise, if you have taken it somewhere over here, okay, you would see this distance as minus D2. As because we have taken it here inside the robot here. Okay, so I don't see any distance here. So that is again the second benefit of it. So that is there. Okay, now theta 3 is the joint angle measured between X2 and X3. That is the joint angle. So you know that. So it is going to move something like this. Okay, so that will be angle between X2 and X3. So if this is your X2, you see you have X2 here and X3 is also aligned on top of it. So both the frames are here and here, you know. So currently this angle is 0 degree, but if this link moves, you see there is some angle theta 3 that will come. Okay. A3 is measured along X3. A3 is measured along X3 between Z2 and Z3. But you see Z2 is like this, Z3 is like this. So this is the distance. So there is a distance over here. So that becomes your A3. That is the link length because that is measured along X3. So this was your X3. So this is your distance, which is A3. Got it? There is no D3, but there is A3. Theta 3 is there. Okay. Now look at alpha 3. Alpha 3. So that is measured along X3. So you see, you have X which is like this. You have X which is like this. To take Z2 to Z3. Now see where is your Z2. This is your Z2. You have Z3 which is here. So you have to measure it like. So this becomes your alpha. So from here to here, that is 90 degree. If you rotate like this about positive direction about x-axis, so it is plus 90 degree to take Z2 to Z3. So alpha 3 is 90 degree. Now the DH parameter is this one. This row has been added now. D3 is equal to 0, theta 3, A3 and 90 degree. Done? Okay. Okay, now the frame placed at the end at the physical joint in second case as shown here, okay, is displaced along Y2. Okay, it is displaced along Y2. So Y2, where is your Y2? So this was your Y2. So if this frame is displaced along Y2, so it will be wrong. You won't be able to find out the parameters. So that would be wrong. So taking that will create this issue later on. So you don't have to take that, and Z3 can be directed opposite as well. Okay, Z3 can be directed opposite as well. So if you have taken Z3 like this, okay, it can be placed, otherwise also both will be the same. So you see, DH parameters can be taken in multiple ways. At least Z axis can be this way, it can be otherwise also. So that is what is there. Even in case of data sheet of this robot, it shows, you see, the way we have taken, the data sheet says something else. So you see, initially we took Z axis vertically upward, but in the data sheet it shows this direction as positive. That means it is into the plane of the ground. Okay, so this is as per the data sheet, but we took it like this because I find it is very easy to understand if you take positive direction upward to the ground. Okay, again, axis 4, you just see this is showing direction something like this. Okay, so this is your direction. So that means it is something like inside, but we took it like this. So again, at the end, you will find a similar problem which is here, that takes end effector frame, which is something like this. Okay, but I prefer it taking forward as positive so that it is very, very intuitive and easy to understand. Doesn't matter, things will take you to the same place at the end. Okay, so be with it. Need not to worry about what data sheet shows, but you have to be very careful when you convert the parameters which are shown by the robot's teach pendant. While you convert that angle, you just have to make it positive or negative accordingly and put it to your DH parameter table. Okay. Now moving ahead, attaching the link 4 now. Okay, so this is your link 4 and I have to put now axis here. Okay, so this was your 0, this is your 1, this was your 2, you have already placed the third one. Now you have to put the fourth frame, that is at the end of link 4. Okay, so I am talking about this. So how it should be placed? So Z4 is along the axis of rotation of link 5. Link 5. So you know link 5 is this one. Okay, so this one. Okay, so axis is something like this. This was your Z3. So this is your Z4. So X4 is common normal to Z3 and Z4. So this is your green one, that is Y axis. This is your z-axis. This is z4. Common normal to z3 and z4 is x4. Okay. And z cross x is y. So this becomes your y4. Got it? So this is how it is placed at the center of the wrist. Okay. Now moving ahead. So D4 is the distance measured along Z3. Distance measured along Z3 between X3 and X4. Now let us find out where is X3 and X4. Here is your X4. This is your X3. So distance measured along them will be D4. Okay. That is measured along Z3. So you know your Z3 was something like this. So this was your Z3. So this becomes your D4. Got it? So this is distance measured along Z3 between X3 and X4, that is D4. Got it? Now theta 4 is the joint angle, that is the joint variable measured between X3 and X4. So this is your X3, this is your X4. Angle between them will be the joint angle, that is the variable. Okay. Now A4. A4 is measured along X4 between Z3 and Z4. So where is your Z3? First of all, this is your Z3. Where is your Z4? This is your Z4. Okay. So distance between these two Z's measured along X4. So where is your X4? So this is your X4. So there is no distance between them. So that is making A4 equal to 0. Got it? Now alpha 4. Alpha 4 is measured along X4. Measured along X4. So this is your X4. Angle between Z3 and Z4. Again, this is your Z3. This is your Z4. Okay. So you see you have to be in the right hand thumb rule. So it should be plus 90 degree, which is coming. This is your angle, that is 90 degrees. So alpha 4 is 90 degree. Completing that, we'll get this parameter. You see this becomes equal to 0, D4, theta 4 and 90 degree. Done. Okay. Now let us put the fifth plane that is attached to the link 5 at the end. Okay. So Z5 will be placed along the axis of rotation that will rotate link 6. So we'll quickly put it. We know that was a small link that is here, you know. This is the small link which is at the end of this link. At the end, this is sixth link. Okay. So we'll put it like this. So this becomes your axis of rotation. This is Z5. Okay. And X5 will be common normal to Z4 and Z5. Got it? So where was your Z4? So this is your Z4. Got it? So that was rotating your link. Okay. And where is your Z5? Here is your Z5. This is your Z5. Okay. So that is also there in this one, but because it is very clumsy out there, so I use this one. So yes, so this is your Z5 and this is your Z4. So now there is a common normal that you can draw common normal outward like this, or you can draw common normal inward. So for no particular reason, so here it is, I have put it like this. So this is your axis, that is your X5. So you have Z5 here, you have X5 here. So Z cross X should give you Y5. And this is not over here, it is actually sitting somewhere inside at the wrist center point. It is over here. Got it? Okay. Y5 is directed along cross product of Z5 and x5. So that is as per right-handed coordinate system you can quickly place. Okay. So d5 is equal to 0. Why? That is measured along z4 between x5 and x4. Got it? x4 and x5. So this was your x4, which is already here, and x5 is also there. Both are at the same location. So that is what is making d5 is equal to 0. Got it? So because there is no distance that is measured along z4. Okay. Again, theta 5 is the joint angle that is measured between x4 and x5. What is there? So you have already x5, you have x4 over here. So there is already some angle which is rotated, which is shown here in this figure. Okay. And anyway, theta 5 is a joint variable. You don't need to put. It can be put just like a variable theta 5. Okay. So A4 is again equal to 0. Why? Because both the location of frames are at the same location. Both the frames are at the same location. So measured along x5 between z4 and z5. So there is no distance between z4 and z5. Got it? So this was your initially z4 and this is your z5. Okay. So there is no distance between them, which is measured along x5. So this is your x5. Got it? So there is no distance. So that makes A4 equal to 0. So finally you have to find out alpha 4. Alpha 4. Where is it and how it is? So it is measured along x5. Measured along x5. Let us first quickly draw where is x5. x5 is here. x5 actually it is placed inside over here, and it is angle between z4 and z5. So where is z4? This is your z4 and z5 is like this, z5. So you have to rotate by an angle 90 degree in order to come from z4 to z5. So that makes alpha is equal to 90 degree. Got it? So finally, if I put them all together over here in this table, so this makes d5 equal to 0, theta 5 is the joint variable, a is equal to 0, that is the link length, and alpha as 90 degree. That makes it complete. Got it? So minded frame is to be placed, as in second case is ambiguous. This makes it quite ambiguous. You have to put the frame exactly at the wrist center point so as to understand it thoroughly. Wrist center point should make all the axes intersecting at the same place, and that forms the basis to rotate the link 6. So I have put it conveniently there. Okay. So anyway, that also will make A5 and D5 equal to 0. That is not an issue. So yes, now the final frame. Final frame, you know, it is to be placed at the end of the final link. So here it is 6th link. So this becomes the 6th frame. So without doing much of an exercise, I simply dislocate the 5th frame that I have put. Okay, so just put the 5th frame, just make some offset and bring it to that place. So that is what we have been doing. So yes, Z6 is assigned along the axis of rotation of the 6th link. So 6th link is already here. 6th link is a very small one, you see. It is just a disc. So that is what is going to rotate. Assigned exactly along Z5. Just bring it downward because that moves in this direction only. Okay, X6 is common normal to Z5 and Z6. Now your X. So this is your Z5. So this is your Z5. This is your Z6. So common normal is making this X6. So this is your X6. Okay. The last frame includes the robot's tool flange in D6. You see there is an offset. You have to travel along Z-axis. So that is capturing the distance, that is D6, which is here from this point to this point. So that is small distance is captured here. Okay, that is to be captured. You should not end your robot's frame right at the wrist center point. You should bring it to the tip of the robot so that you can ultimately, when you do forward kinematics, you will get the end effector position, not any intermediate position. Okay, Y6 is directed as per right-handed coordinate system. So D6 is measured between X5 and S6. So as we did just now, X5 and X6. Here is your X5, this is your X6. Distance between them measured along Z5. So this is your Z5. Got it? Theta 6 is the joint variable that is measured between X5 and X6. That is the joint variable. So forget it. That is just a parameter which is a variable. A4 is equal to 0 because it is exactly in the same line. So there is no offset between Z5 and Z6 measured along X6. So that makes A4 equal to 0. Alpha 4 equal to 0. Again, it is measured along X6 going from Z5 to Z6. Z5 and Z6 both are in same line. So there is no angle between them. There is no twist for the sixth link. So that is exactly making alpha 4 equal to 0. Now the DH parameter table is complete. Okay, I have put all the variables here and this makes it complete. So an additional tool frame transformation, sometimes you have an additional tool frame. So sometimes maybe you have a link which is coming even after this. You can put a frame directly over here instead of putting at the tip of the flange. Okay, so that will give you the end effector pose. So that distance also you can already take into consideration while making your DS parameter. But normally when the robot is delivered, it is delivered like this and it is quite okay. Okay, now let us populate this DS parameter table using the technical specification which are given in the manual. So you have to just put the distances as it is given in the data sheet. So I'll just copy them from here. So you see it is 400, that is the offset. Offset from this point to this point. So you see it is 400. Now theta 1 is the joint variable. 180, that is distance between this and this going from this distance. So this distance is 180. Alpha is from the DS parameter table. This was 0, now 600. 600, that is distance between this and this. Okay, so that was making it 600, that is distance between two Z axes. And again 120, this is the distance. This one you see. Okay, 620 is here, that is from the wrist center point to the frame which was placed here. So that is the distance. It was measured along Z axis. That makes it a offset, joint offset, not the link length. Link length was 0. Fifth one, both were 0. Sixth one, it is distance which is here. So that is taking it to the flange tip center. Okay, so that is 115. So that is here. So that comes here. So you got it. So you can directly create a DH parameter table in terms of variables and later on you can put it the way exactly as it is in the technical specifications of the manual, or if possible you can measure it, that is fine, but that will be quite inaccurate. Okay, so this is it. So this is how you have to do forward kinematics. At least for this position, if you do forward kinematics, you will see you are getting a homogeneous transformation matrix which is like this. Okay, so you can verify this using one of the situation. Okay, instead of verifying the end effector poses for position and orientation, it is easy to take it to a position where you can directly calculate using the parameters which are given in the robot's manual. So you know the link lengths, you take it to a position where you can directly calculate your end effector position and see whether your forward kinematics is also giving you the same result. So at least for this one I know it is distance which is 180 plus 620 plus 115. So this was 115, this was 620, and from this to this distance, you know, it was already 180. Okay, so total distance which is here is x like this, and then about y, because in this particular position y is coming out to be 0. But if you rotate axis 1 by 90 degree, so this face will go to this direction, and in that case it will become same 915 will be visible along y-axis, not along x-axis. Okay, in that case x will become equal to 0. Got it? So now take the height, that is z. So it is 400, that is distance from ground level to this level. So that was 400. 600 was the link length from here to here, that was 600. Okay, now 120. 120 is from this distance. So this was your 120. So that is your 120. So 400 plus 600 plus 120, it comes out to be 1120. So that is what is the Z location. Okay, so that is your Z, this is your Y. Got it? So directly you can verify your position, at least for few standard positions where you can easily calculate manually also. Okay, orientation can be seen at least in this pose where it is now. You see U is the projection of U, that is this frame. This is your U, this is your V, and this is your W. So projection of U along X. Along X it is. So where is your X? This was your X. Right. So you have, this was your Y, X, Y, and this was your Z. So just compare how is your U, V, and W oriented with respect to X, Y, Z. So this is exactly the orientation matrix. So at least for U, you see, it is coming out to be 0, 0, 1, because U is now directed along positive Z direction. Positive Z direction, you see. So exactly it will be 1. Similarly, V will be, V is in this direction, you see. Okay. So V comes out to be 0, minus 1, 0. Y along X it has 0, along Y it is directed opposite. So it is minus 1, and finally along Z it is 0. Now finally W. W is as it is. So U, V, and W. W is like this. W is pointing directly towards X, so it becomes 1, and rest 2 will be 0. So one of them, if it comes 1, remaining will automatically be 0, because it is a unit vector that can be 100% along one direction, then it is in other direction it will be 0. So that's all for this. Try to verify this forward kinematics using your own MATLAB code, or maybe any programming language you are familiar with. Okay, so that's all for this. Thanks a lot. So in the next class, we'll be doing inverse kinematics and differential motion analysis. That is the module that we will be starting. That's all for today. Let me say thank you this way. So we are done with industrial robot forward kinematics. This is what at least you also can think of generating in your own programming language, maybe MATLAB or Python or C, whatever you are familiar with. That's all. Thanks a lot.